Today, transportation plays an essential role in our everyday life, especially in urban areas. For example, public transportation provides an affordable way for people to go from one location to another. In cities, there are many modes of commuting people can choose from, ranging from driving personal vehicles, taking buses, going on trains, or riding bicycles, and so on. When people select what form of transportation to take, they must go through a process of identifying the risks, weighing the benefits, and assessing convenience. Due to the reasons just mentioned, it can be assumed that there is also a varying level of stress associated with each commuting type. This report is designed to provide an insight to understand the degrees of stress experienced by different groups of commuters. The two populations we will look into in this study are drivers and non-drivers. My goal is to identify the difference in stress levels, or if there is a difference at all, for the two groups. The problem we'll investigate here is if driving can cause more stress as opposed to other modes of transportation in the city. Why I am interested in this topic is because it is evident the common stressors for the commuters' population, such as being stuck in traffic, having the risk of accidents, and being exposed to vehicle pollutants. I believe it is important to identify which commuting mode causes a higher stress level so that there can be action taken to improve the current transportation infrastructure in the city where this study's data was sampled. Diagnosing the higher stress-inducing commuting type can lead to conversations being had that lead to policies aimed at decreasing worries for the people who commute, assist with a part of their mental health, and ensure a sense of well-being. The results of this study can hopefully lead to a step closer towards the right city planning decisions. For the objective of this project, our goal is to identify if there is a difference in stress level between the two sampled groups, drivers and non-drivers. Also, to infer whether the commuters that drive would report a higher stress level than those who do not drive. To analyze the data sets from our two groups, with Population 1, for drivers, and Population 2, for non-drivers, I used our programming language to apply the Mann-Whitney U or Mann-Whitney-Wilcoxon non-parametric hypothesis test. After looking at the overall data from each Google survey response, I extracted the data values onto Excel and stored it in a spreadsheet for the R code analysis. To check visually whether our data was normally distributed, I coded a histogram for each group's dataset, non-driver and driver. The histogram for the driver's dataset showed a relatively symmetric distribution where the two tails at each end of bell-shaped peak had similar heights. To confirm the data distribution normality, a Shapiro-Wilk test was performed in R with the rule that if p-value output from the test is larger than 0.05, then the data is normally distributed, and on the other hand if the p-value turned out to be less than 0.05, we can conclude that the population's dataset are not normally distributed. In Figure 1, one of our datasets, the non-driver population has a p-value of 0.002292, which is less than the significance level of 0.05. Therefore Population 2 has data that is not normally distributed and would require a non-parametric form of testing. Drivers' population's p-value result from the Shapiro-Wilk test is 0.186 in Figure 1. This is more than 0.05, meaning this dataset is normally distributed. Given that all the data are ordinal, because each respondent reported their average stress level values on a scale from 0 to 5 related to their commuting mode, I went ahead and continued with the Mann-Whitney U test, a non-parametric form of testing, for the rest of the study. My two-tailed test's null hypothesis states that Population 1 drivers will be identical to Population 2 non-drivers in terms of stress level values from the survey. Each data is assigned its own rank based on its order of magnitude relative to the rest of the data values within the population's dataset. For the upper-tailed test, my null hypothesis is that Population 1 drivers will have lower stress level values than Population 2 non-drivers. To test these hypotheses, the rule for the Mann-Whitney U test is that if the R code outputs a p-value of less than the significance level of 0.05, then we can reject the null hypothesis. For testing this Mann-Whitney U test, the only difference between the Wilcoxon test for two-tailed and upper-tailed in the R code line is shown in Figure 3, with the upper-tailed one specified with alternative greater. From Figure 4 and Figure 5, it is observed that the histogram of the driver's group looks relatively symmetric, whereas the non-driver's group looks skewed to the right. I also generated a box plot in R to analyze the data within its own groups and between the two groups. With the data collected from the sampled 42 respondents, the box plot, Figure 7, provides a visual summary of the descriptive data. From Figure 7, the two boxes are sort of overlapped, but the median of the two groups is different, which tells us that there are variances between the two groups, again, drivers and non-drivers. From Figure 6, it is observed that for the drivers group, the median stress level is 2, ranked on a scale from 0 to 5, and the maximum stress level is 5. However, for the non-drivers group, the median stress level is lower, which is 1, and the maximum stress level is only 4. The result for the first test, the two-tailed test, is to see if we should reject the hypothesis that the two populations, drivers versus non-drivers, will have identical stress levels. The p-value from this test, the Wilcoxon test, is 0.01958, which did not reach the significance level of 0.05. This allows us to reject the null hypothesis. The result for the upper-tailed test is to see if in population 1, the drivers will experience a higher stress level on average than population 2, the non-drivers. The final p-value for this test is 0.009791, Figure 9, which is less than the 0.05 significance level. This test's results allow us to reject the null hypothesis that population 1 is less than population 2, therefore accepting the alternative hypothesis. After looking at the results, it is evident that we can reject the null hypothesis, which would mean the driver group and non-driver group are not identical. Based on these results, we can conclude that the driver group experiences higher stress levels than the non-driver group. Thus, I can recommend that the Department of Transportation of the City of San Jose, the location where this data sampling took place and the survey respondents are majority from this city, should focus on further improving the transit app as well as increasing the number of parking lots and allocating more parking permits. Currently, this app displays the timings for all trains, but it is very apparent that the app does not provide any updates when there is a change to the schedule. Therefore, I believe it would be extremely helpful if they could incorporate a system that provides more accurate updates regarding delays, cancellations, and any other potential problems. By making these changes, public transportation would be far less stressful as a large majority of the information would be accurate. Moreover, this will help more people convert to public transportation over driving when choosing a commuting option. Along with this, building more parking lots and allocating more permits would further reduce stress for drivers as they would not have to worry about finding parking. The two populations in this study's analysis, drivers and non-drivers, do not have identical stress levels, a major lesson learned from the results. Additionally, we learned that drivers experience higher levels of stress than non-drivers, based on the data we've gathered from the survey and Nhi U test. Thirdly, we discovered that our data is not normally distributed, so with a little bit of research I found that the non-parametric testing method would be best to apply to the data, instead of the normal parametric testing methods. There were a few initial challenges going into the study. The first is about data distribution and knowing what correct testing method to choose. There is parametric or non-parametric hypothesis testing. I was able to solve the challenge by putting the data set into a histogram function for a chart output in R, which confirmed that the data distribution is not normal, meaning a non-parametric testing method must be used. I decided on going with the Nhi U test, a non-parametric testing technique that was successfully used to analyze the dataset. Thank you. This research was done with the interest to explore the topic of human stress levels associated with city transportation. Inspired by a series of sources ranging from published books, journals, to internet videos. Study, essay, and script by Nhi U. Huynh.